Last time we started talking about alkenes and alkynes. So remember, as we talked about, these guys have functional groups, and the functional group is the carbon-carbon double bond for the alkenes, and it is the carbon-carbon triple bond for the alkynes. Remember, everything is named, excuse me, named just like they are for the alkanes, except we do change a couple of things. We still look for the longest carbon chain. And that longest carbon chain does need to contain either the double bond or the triple bond in it when you are counting it. We give the priority in terms of numbering to the double bond or triple bond. And depending on which way you name it or number it, everything else that's attached will be numbered accordingly. We do change the name. So if it has a double bond, it will end in ENE. And if it has a triple bond there, it will end in YNE, as to how we go about naming those guys there. All right. So I think that's about where we are. So the IUPAC way of naming, again, as I mentioned, we do the ENE if it's a double bond, the YNE if it is a triple bond. These guys in parentheses are common names, but we'll go by the IUPAC name for those guys. If it is pretty much kind of like 3 or more carbons, you do also have to give the location of where the double bond or triple bond is located. In the case here of ethene or ethyne, there's really only one place where that double bond could be located. But if we did have something like this, here we would have 1, 2, 3, 4, 5 carbons, which is based off of pentane. Has a double bond here, which then makes it pentene, ENE. And the location of that double bond would be carbon 1 and carbon 2 coming this way. Going the other way, 1, 2, and 3. So 2 is the smaller. So we would go with 2-pentene. The reason we need to do that is if we had, for example, the double bond up front here. This now would move the double bond to carbon number 1, and this would be 1-pentene. So whenever around 4 carbons or so is usually 3 or 4 carbons is where that comes into play, and you just give the location of where you find the double bond or the triple bond in terms of its location. Any questions on that there? Okay. So why don't we try some here? So why don't you give the names for each of these, and why don't we also do some that we draw? Let's do 3-methyl 2-hexene. Let's also do something. I don't know. Let's do 2-bromol 4-pentyne. All right. So why don't we draw these guys and name these guys here? 2, 3, 4, and then down would also be 5. So again, you could go either way on this. I'm going to take the straightest way, which is not that. There we go. Something to work with. There we go. Okay, so we got 5 here, which would be pentene, ENE, as it has a double bond. It also has this group hanging off of it, which is a methyl group. We want to number the way that will give the double bond the smallest number, and that would be going 1, 2, 3, 4, 5. That means that this would then be 2-pentene. And because we locked in our numbering going this way, that means our methyl would be at carbon number 4. So it would be 4-methyl 2-pentene. Yeah. Any questions on that one there? Okay, looking at the next one here, we got straight across, I'm thinking here. So 1, 2, 3. There is one there, which is 4. There is one there, which is 5. And there is one at the end there, which is 6. So that is 6 carbons, which would be based off of hexane. Here we have a triple bond happening. So then that would then become, that would become hexine. And our triple bond would actually be a carbon number 2 heading in that direction. So this would be 2-hexine. Any questions on that one? There you see the triple bond in the linear geometry, right? So it kind of flattens out because of the geometry that's happening there. Any question on those two? All right, so we're going to draw some here. So we'll work backwards from the name. So starting with the back part here, that is hexane basically. So that's 6 carbons. So 1, 2, 3, 4, 5, and 6. It is a ENE, which means it's a double bond at carbon number 2. So for me, I'm going to call this guy carbon 1, which means my carbon 2 would be right there. Again, you could do it on the other side if you wish. Because I did call that carbon 1 and that carbon 2, that means carbon 3 for me would be right next door, where there is a methyl group. And the rest at this point would just be hydrogens. So this guy needs 3, 2, 2, none here. That's 4. This guy needs 1 if I squeeze it in there, and this guy needs 3 going on there. Any questions on that there? Yeah. Yeah, you could do line structure. Are you asking, would you do the same approach if you were drawing a line structure? Yeah, you would. So if we were doing line structure, we would just start with, let me clear out a little spot here to do it. So you would do really the exact same approach. So you start with the hexene, which means you need to basically draw the 6 in the line structure. 2, 3, 4, 5, and 6. You then would go to 2. So once again, that would be carbon 1 for me, which means carbon number 2 would be here, and you just put a double bond right there. And then at that point, since that's carbon number 2, carbon number 3 would be here, and you would have a methyl group coming down like that. Any questions on that? So you do basically the same step no matter what type of structure you're drawing. Even the expanded structure, it's basically always want to work backwards. Yeah. Other questions on that? All right, so again, working backwards here, that's pentane, which is 5. And YNE is a triple bond, and it is at carbon number 4. So again, I'm going to call this number 1. So 2, 3, 1, 2, 3, and 4. That's how you count. There we go. That is a triple bond there. That takes care of that. At that point, since I have this as carbon number 1, my carbon number 2 would be right here. And once again, here we'll just fill in our hydrogens. So that needs 1. This guy needs none. This guy needs 2. This guy needs 1. And again, we want to get carbon to 4 bonds. So that one needs 3. And once again, if you were doing your line structure, you could do it the same thing. 1, 2, 3, 4, and 5. And again, 1, 2, 3, 4, you would do your triple bond like so. And then 1, 2, you could do your bromine. Now, I'm okay drawing it like that. I know sometimes they'll draw it with the geometry flat out. It's okay with me if you draw it like that, without the geometry sort of showing you. Any questions on any of those there? Just get out of the way, huh? All right. All right, so let's also talk a little bit about cycloalkenes. So cycloalkenes are really like cycloalkanes, but they do have a double bond in them. So you can have this sort of ring structure where you do have this sort of double bond located. So you name it the same way. You do it based off of the cycloalkane name, but you just put ENE at the end of it. There is a little situation that you have to do when you do have things attached. So for example, this would be cyclopropene, ENE, because of the double bond that is there. You would not need to give the location of where the double bond is because it's assumed to be carbon number 1 wherever it's at. But if you do have something attached, like we do see down here, oops, or we draw it up here. Got this going on, and we got this going this way. So we do need to give the location of this group that's attached. This first off would be 5 carbons, which means this would be, as it says there, cyclopentene, ENE. Once again, you do not have to give the location of where the double bond is located, but the double bond is definitely going to be carbon number 1. So we want a number, whichever way will give the group the smaller number. So there's a really important rule, though, which is you may think, well, if this is carbon number 1, I could just hang to the left, and then that would be at number 2, which would be a small number. But the rule is when you do have a group attached to a cycloalkene, you have to number and go through the double bond. So you have to number and pass through the double bond as you are numbering, which means you cannot actually just go that way to give it the smaller number. So really your 2 options would be in this particular case would be to go 1 and go through the double bond to 2 to 3 to 4 to 5. The other option would be to start at carbon number 1 on this side of the double bond and go counterclockwise through the double bond to carbon number 3, carbon number 4, and carbon number 5. So in this case, the one that would give us a smaller number is actually starting with this guy being carbon number 1 at that side of the double bond and going counterclockwise. And that's how we get to 3-methyl cyclopentene. So you got a number starting at the double bond, you have 2 ends, but you do have to kind of go through the double bond with the next number one way or the other, and whichever way gives you the smaller number. Any questions on that there? Okay, so let's see here. Why don't you give these guys a go, see what you come up with. Why don't you also draw 2 chloral 3-methyl cyclo something, cyclo something. Actually, let's do, I'm changing my numbers. I'm changing my mind here. Let's do 3 chloral, 4-methyl, still cyclo something. Cyclo, let's do, so the entire thing, 6 carbons, so cyclohexane. We have a double bond, so it's going to become cyclohexene. Again, no need for the number as it's always considered carbon number 1. Coming to the next one here, this whole thing here would be our biggest carbon chain, and that would be 5 carbons, which would then become cyclopentene, as it also has a double bond. We also have basically 2 methyl groups hanging off of there, right there. So we have a dimethyl situation here. And now for our double bond, we really have 2 options. We could go 1 here, then we got to go through the double bond. So that would be 2, 3, 4, and 5. The other option, I'll do it inside, 1 here, going the other way, 2, 3, 4, and 5. So in this case, it is clockwise that does give us a smaller number. And in this case, it's actually a double 3 there. So that's going to be 3,3 dimethyl cyclopentene. Any questions on either of those two?
So if it's a complete, whether it's a triangle or a square or on there, no matter what, anything sticking out, it'll never start from that point. Because if you look at it, if we went one of the lines out,
Yeah.
it would be 6.
Yeah, no, it will not. So because you have basically that cycloalkane or alkene, that really is kind of your main sort of part of the molecule. So anything that would be, like you said, sort of attached to it would be considered a group in most cases. Yeah. No, because again, it's a ring structure, so it's assumed wherever that double bond is will be carbon number 1. So you don't need to do it. Yeah. Other questions? Okay, so working our way backwards here, we got cyclobutane. That is a square, just 4 carbons. So really, you can put the double bond wherever you like. So I'm just going to put it up on top. But honestly, you can put it wherever you like in the square, basically. Wherever you put it, you're going to call one side carbon number 1. So for me, I'm going to call that number 1, which means I'm going to go through the double bond to carbon number 2, going clockwise, 3 and 4. And that's going to give me the proper locations to put everybody else. So we'll do a line there. We'll do a line there with a chlorine, basically. Yeah. Any questions on that? Yeah. What's that? It should say butene, unless I wrote it wrong, but that was supposed to be an E there. You know, it's like an A, it's a vowel. It works on Wheel of Fortune. It's all right. But yeah, no, it should be not cyclobutene. Yeah. Question on cycloalkenes, how to name those guys, draw those guys. Okay. All right, so let's talk a little bit about isomers. We did last time as well. So remember, isomers are really they have the same molecular formula, but they do have different connectivities. And a certain thing occurs with double bonded compounds. And that is, once you double bond it, pretty much these carbons are locked into place. And that's different than what happens when you have an alkane. That carbon is pretty much free to rotate everywhere you like, which is why oftentimes we go, yeah, you can draw it up or you can draw it down. It really doesn't matter because it has free rotation around it. When you get that next bond in there, it pretty much locks everybody into place. The result of that is there are certain groups that they're called get locked into kind of one side of the double bond or the other side or opposite sides of the double bond. And that leads to what are referred to as cis or trans isomers. Cis meaning that they are on the same side of the double bond. Trans meaning that they are opposite sides of the double bond. So cis or trans can basically be found by that. By the way, cis, if we take the thumbs, it should be up. Or you could have the thumbs below the double bond as well. They're both cis. And opposite thumbs here would give you your trans sort of arrangement. Now, there's a few things that you have to have in order to even have the possibility of cis or trans. And it really does all focus in on the double bond. So when you look at the double bond, they will have what are referred to as groups attached to them. And we'll just call this guy A, and we'll call this guy B. when you look at the groups on the same carbon and the double bond, they has to be different. So for example, here, these two guys are different. So if you should by some chance come across a double bond where you have two groups that are basically the same on the same double bond, it is impossible to have a cis or trans isomer happen. So that automatically like eliminates the possibility of cis or trans occurring. But if you get to this point where you do have different groups attached, the other thing that you need is a group that is the same on opposite carbons. So in this case, there's an A there and an A there. Those are the same group on opposite carbons. By the way, you could have two same groups on opposite carbons, but you got to at least have one group that's the same on opposite carbons. And those are the ones that you want to look at to determine cis or trans, which in this case it would be. The A group there is on opposite sides of the double bond. This would be the trans isomer in this case. Yeah. Any questions on that there? So if we look at the bottom here, we got a chlorine and a hydrogen, which is different. And in the case of doing cis and trans, we do kind of consider hydrogen a group, kind of the only time. So it can just be a hydrogen, look at hydrogens. We have a chlorine and a hydrogen, which are different. And in this case, we do have the two chlorines that are the same on opposite ones. And in this case, they are on the same carbon. And that would be the cis isomer here on the left. Same thing here. We have different groups. And again, the same group, the chlorine on opposite sides. And this guy would be the trans isomer. First off, any questions on that there? Now, a really important thing is this. So I'm going to erase what's on top and I'll just steal what's on the bottom there. So we'll steal the Cl to the C, the C to the Cl. Actually, I'm going to change it just a little bit. Going to do an H, do a CH2, CH3. Okay, so if we look at this one here that I just drew, by the way, this would be cis or trans. This one should be this. So we would isolate the double bond. Once again, this group and this group are different on that carbon. This group and this group is different on that carbon. But the group that is the same on opposite carbons, again, is the chlorine here. And they're both on the same side of the double bond. So this would be cis in this case. Yeah. Any questions on that one? All right. So the real reason I drew it, let me now erase all that stuff I just read. There you go. So we can get to the real reason I kind of drew it. And the real reason I drew it is when people are asked two things. First thing is to name it. When people see something drawn like our cis or trans, they're oftentimes focused in on the double bond, which is important. But the longest carbon chain here is how many? It is not just two. It is 1, 2, and then I got 3, and then I got 4. So when people see them drawn as cis or trans, they focus so much on the double bond that everything they name is ethene, because there's always just 2 carbons in the middle there. But you still need to look for the longest carbon chain, which in this case would actually be, what did I draw there? 4, I think, right? So this would be butene. We would also still need to do the same thing, which means this actually would be carbon 1, and this would be 1 butene. And this would be 1 and 2 dichlorobutene. I run out of room as I try to squeeze that in. We'll start back a little further. This would be 1,2-dichloral, 1-butene, and we would then put cis in front of it. So this would be cis. 1,2-dichloral, 1-butene would be the proper name, not ethene. Yes. Yeah. Yeah. Oh, do I? The one I just made up? Oh, okay. Guess I was just ahead of the game there, I guess. Yeah. All right.
Basically, it's the C8 that hydrogen carbon.
Are you asking like at the end, sometimes they'll write it like this, or sometimes they'll write it like this? Is that what you're asking? Yeah. Yeah, it is the same thing. Sometimes people will write it like this to indicate that it really is, again, the carbon and carbon that's bound to each other. I personally don't care if you do it either way, but that's why some people will do that to show, it really is the carbon to carbon. So there's no misunderstanding that it's like the hydrogen to the carbon being connected here, because it really is the carbon to the carbon. But you can do it either way, if you like. Other questions on that? So that is a very common way that sometimes people will kind of write the ones at the end, just to indicate that, again, that's the carbon to the carbon that's being attached. Are we talking over here? It would be, yeah. Which one are we talking about? Is it a few slides down, or? Right here. Which one are you talking about? The first one, or you're talking about this one here? Yeah. So the 3 goes with the hydrogen to the left. To which carbon? This carbon?
Yeah.
Yeah, but this carbon is only directly bound to this carbon. And then these 3 hydrogens are attached to the one at the end.
Okay.
Yeah. No problem. Other questions on that? All right. So let's head back there to see what we maybe went over there. All right, there. So we got more fingers. All right. So cis-trans, you could do your fingers, I guess, to make it. As I mentioned, when you go to draw one as well, so let's just say we were asked to draw this guy here, and this is it in line structure, a cis versus a trans. But let's just say we were asked to draw cis 1,2-dibromo ethene. I personally would recommend, if you're asked to draw it, to just draw it without the cis and trans part, and then draw a second structure where you do make the cis or trans. So for example, if I was to do this one, I would just do it like normal. So ethene here is just 2 carbons. And we'd have obviously our double bond in that particular case. And dibromo, so we would have a bromine at carbon 1, bromine at carbon 2, and then we obviously would have a hydrogen as well. So once you sort of have the whole picture drawn, you could then just redraw it, starting with the carbon-carbon double bond, and you could basically accentuate what it should be, which in this case, it should be the bromine on whichever side of the double bond you want to put it, and then the hydrogens on the other side. So a lot of times it's easier just to draw it without like the cis or trans part. Once you get sort of the proper drawing, just redraw it, starting with the carbon-carbon double bond. And then if you need to put one group up and one group down, do that, and then put the other guys on the other side. And that's a much easier way to kind of draw it, showing cis or trans if you need to, rather than trying to draw the cis and trans right out of the box and try to figure out, what goes up, what comes down. Just draw one structure like normal, and then kind of readjust it for cis or trans. Any questions on that there? Okay. So let's name each of these and then also decide cis or trans in these guys as well. Different, which is good. That and that is different, which is good. And we have a chlorine and a chlorine, which are the same. And we have a methyl group and a methyl group, which are the same. You could choose either one to look at. They are both on the same side. So that should be a cis in this case. Taking a look at this double bond here. Once again, different and different, different and different. This guy and this guy are the same, which you can stop right there. They are on opposite sides. That would be trans. You could also look at the bromines, which are also on opposite sides, which would be trans as well. Any question on those two? Coming to here, different and different, different and different, methyl and methyl the same on opposite sides. And that would also be a trans, yeah. Any question on identify cis or trans in either of those, yeah? All right, then let's talk about the naming part. We're gonna look for the longest continuous carbon chain. And since I got the highlighter, we're gonna do them all here at once. So starting here, actually, that's 1, 2, 3, and 4. Up here, that is 1, 2, 3, and 4. And right there, that is 1, 2, 3, and 4. So they all basically have 4 carbons. Remember, the chlorine here is not a carbon, oftentimes mistaken for it. All right. So now that we have our longest carbon chain, which looks like it is the same in each of these, that is 4 carbons, which means the base of each of these names should be butene, right? We want to give the location of the double bond, and it looks like in each of these cases, 1, 2, or 1, 2, if you go the other way, doesn't really matter. 1, 2, and 1 and 2. So it looks like they're all really at carbon number 2, no matter which way you go. Now, starting with the first one here, the actual groups that are attached are actually only the chlorine groups, as the methyl groups there are actually part of the longest carbon chain. And that means that we have 2, 3 dichloryl 2-butene, and we would then put our cis in front of that. Yeah. Any questions on that one? Coming to the next one, also looks like it is 2, 3 dibromal. And then this guy would get the trans. And lastly, here we have trans 2, no 2, no 3, nothing, just trans. There are actually no groups attached there, right? Everything else is hydrogen in that case, which means it is just trans 2-butene in this case. Any questions on either of those names or any of those names? So if I had this would be cis or trans? Or neither. It is neither, yeah. So this is our double bond. This and this is the same, which automatically eliminates the possibility of cis or trans because those two groups are the same. And you also don't really have 2 groups on opposite carbons that are the same either, right? So this one would not be a cis or trans possibility. Any questions on that there? Okay. So let's talk about the major reactions that alkenes go through. They go through what are referred to as addition reactions. And that's different than what we saw with alkanes, which do substitution reactions. In a substitution reaction, somebody goes off, somebody comes on in its place. In the addition reaction, everybody just comes on. Nobody goes off, basically. Everybody just comes on and joins the party. So in these addition reactions, you pretty much always have a carbon-carbon double bond, and you're going to add something to it. Maybe it's two things that are the same. Maybe it's one thing that's the same and something else is different. But pretty much 100% of the time when this reaction occurs, you really should only be focused in on pretty much one spot. And that one spot is always, when you're doing reactions, the functional group. So that is really the only spot of the molecule that's frankly going to change. Nothing else changes, everything stays the same. And when we do these type of reactions, pretty much this is what happens. I'm going to put the arrow back over here. Nice arrow, I like it. Not what I was going for, but we'll go with that. Pretty much what happens is, at this point, if I wanted to attach into my molecule the way it stands, like this, and if I wanted to put an A onto this guy and an A onto this guy, I could not do it because that would definitely give carbon way too many bonds. So what happens in these reactions is, before those guys come in, we pretty much have to make some room for them. So we can't do that because too many bonds is going to happen. So what always happens is our double bond becomes a single bond. And now you'll have room for it. So we take our molecule exactly the way it's drawn. Nothing funky happens. Yes. Stays exactly the same. And now each of those carbons actually has room for what's coming in. And each carbon will get a guy that will come in. So whatever is coming in will go to two different carbons. But you do need to make the double bond into a single bond to make room for it. And then you frankly just put one on one carbon, one on the other carbon. There is a couple of rules as to how that goes in some cases. But in most cases, that's pretty much what happens. This is always what happens when you do a symmetrical addition reaction. A symmetrical addition reaction means that you're basically adding the same thing, like H2, which is what this is showing here. That's what's known as a hydrogenation reaction when you add H2. It is, you know, how you get margarine, basically. Yeah, you get rid of some double bonds and it becomes more solid as opposed to like an oil and stuff like that. Basically, that's why it says it's partially hydrogenated. That's basically what that means, is it does this bond. So we could do these reactions, basically two types of these reactions. We can have something like this here. And that's too many hydrogens. There we go. And we could add something to it. We could add hydrogen. You could add, like, say, Cl2, make it something different than hydrogen. So basically, when we add Cl2 to this is a symmetrical addition. It's basically Cl and Cl is basically what we're adding. So once again, all you should focus in on is this part. And you literally should copy what is there. Don't make it hard for yourself. Just copy what exactly is there. And all you have to do is turn the double bond into a single bond. So I'll just copy it right here. We're going to do this. We're going to do this. We're going to turn our single bond, double bond into a single bond. And now each of those carbons basically has room for the chlorine. One chlorine to one chlorine to the other. And that is the structure that you should end up with. So addition reactions, double bond to single bond. Everybody gets one guy on each of those carbons. That was the double bond. And you put it in there. Hydrogenation reactions when we add hydrogen, which basically means each one gets a hydrogen. Hydration is when we add something like water to it. Any questions on that there? All right, let me see here. We go. So let's talk a little bit about. I'm just going to use the paper here, I think. Yeah, this actually, just do that real quick. Keep it. There's some slides in. There you go. All right. Now I got something to write with. All right. So let's take a look at these addition reactions here. So if you take something like this, and we add hydrogen to it, which is a hydrogenation reaction. Again, when we add hydrogen, we're basically adding two hydrogens, basically. So once again, we draw this, the only thing we're focusing in on is this part right here, and we're just going to turn it into a single bond. I am literally going to this exactly the way it is, going left to right, just turning the double bond into a single bond. Once again, when these reactions occur, no magical chemistry happens, that weird things, and it becomes a ring or something like that. Doesn't happen. Yeah. So just copy exactly what you got there. Double bond now going to be a single bond. And we're going to copy everything exactly the way it is. Once again, we've now made room for the two hydrogens. We're just going to put a hydrogen on one. I'll make a blue and a hydrogen on the other. So we go from an alkene in this case to an alkane. So it's how we get rid of double bonds. It's through a hydrogen, get rid of the bond. If you remember how we make the double bond or triple bond was you get rid of hydrogen, right? To make the double bond and make another double bond or make a triple bond. So to put it back together, we put the hydrogen back in, which is known as a hydrogenation reaction. Again, you could do this with anything. You know, you could use some bromine if you like in certain cases under the right conditions. Once again, the only thing that's going to change is right here. We're going to copy it exactly the way it looks. And now I have a spot for one bromine here and a spot for one bromine there. Yeah. And again, that's what we get here. These are what I referred to again as symmetrical. Addition reactions, because again, you're adding the same thing. So you can't really screw up unless you put it in the wrong spot. But if you put it in the right spot, everybody gets the same thing. So you don't have to worry about choosing who gets what. It's the same element goes to each carbon. And that's basically symmetrical addition. You do need sometimes a catalyst and stuff like that, like it showed on that previous slide, like platinum or something like that. Sometimes you might need a strong acid, but they really don't participate in any of the reaction. It's just there to make it occur a little bit faster. So let's talk though about addition reactions that are unsymmetrical addition. So an unsymmetrical addition you're adding two things that are different, like water, which is H2O. When we add water in these reactions, we think of it as HOH. And this is what is sometimes referred to as a hydration reaction because we're adding water in there. We can also add things like HBr, HCl, where we're adding a hydrogen and Cl, hydrogen and bromine. It works basically the same way if there are no options. So for example, we take our same guy here and we add water which once again is H and OH. So in this particular case, we're again going to focus in on right here. We're going to turn that into a single bond to make room. Just going to copy it exactly the way it looks. Not going to change anything other than the double bond to a single bond. And then that now leaves room for one carbon to get the hydrogen and one carbon to get the OH here from the addition of water. Yeah. We go from an alkene in this case to an alcohol. So this is an alcohol. It has the OH group attached there. So that is one way that you make an alcohol is you take an alkene and you add water to it, and you basically do a hydration reaction and you'll produce an alcohol in that case. Same thing would happen here if we added something like HCl. Works the same way. HCl, we're adding H and Cl. Once again, it will be our double bond that will turn into a single bond. And in this case, that will then open up space for a hydrogen here and a Cl here. By the way, in this particular two examples, it doesn't matter which carbon you put the hydrogen on or which carbon you put the Cl or OH on, because if we went to name this guy, this would be 1-chloroethane, 1-chloroethane, or really chloroethane, no matter what, because it's really going to be on either one. So this would be chloroethane. And if you did it the opposite way, where you put the Cl on this guy, and you put the H on that guy, this would also be the same name because it moved out to that side, which would be 1-chloroethane, or really just chloroethane in this particular case. So in this case, there is no difference where you put the hydrogen and the chlorine, or the hydrogen and the OH if it was water. There is a difference, though, when you have multitude of carbons. So sometimes it does make a difference as to how you add them. So let's take a look at an example of that, which is excuse me. See that. Okay. Now, even though this thing looks a lot bigger, the only thing that's going to change once again is here. That should be the only focus that you have. So let's say we added water to this. We're going to redraw it twice. I'm going to redraw it twice to give us our two options that could happen. But the only thing that's going to change is double bond to single bond. So I'll just redraw it underneath. And all I'm doing is copying what's above, making that into a single bond. And I'm going to do it twice, because in this case, there are a couple of options as to how we could end up with here. Okay, so option number one is we could put the hydrogen here, and we could put the OH here. Option number two is the opposite. We could put the OH here, and we could put the hydrogen here. So in this particular case, we actually can get two different answers. And there is a rule that you should follow in a situation like this. It's what's known as the Markovnikov's rule. And it says that the hydrogen that's being added should end up at the carbon in the carbon-carbon double bond that had the most hydrogens to start with. So when you have a addition reaction like this, and you're adding hydrogen and something else, the hydrogen should always end up on the carbon that started with more hydrogens to begin with. So what that means is we want to go back to our original guy. This carbon has how many hydrogens directly attached to it? 1 and 2. This carbon directly attached to it has how many hydrogens? 0. There's no hydrogens attached to it. These hydrogens are attached to this carbon. So that carbon up on top has none. Which means the hydrogen should end up over here. At the carbon that started with the most hydrogens, which would be the one on the right. This would be what is referred to as our major product. This is what is sometimes referred to as the minor product. You should always draw the major product is usually what you should always draw when you're doing this. So whenever you have these unsymmetrical addition, and it does make a difference, hydrogen should always end up on the original carbon that had the most hydrogens to start with. Any questions on that? Okay. So why don't we try some here? Let's just randomly draw some things. All right, let's do this. Let's do this. All right, let's add HCl. Let's do some H2. Okay, so take a minute or two and draw the results of each of these reactions here. Okay, let's take a look. So once again, in all these, even if they look weird, they look strange, they look big, the only thing that changes right there. Yeah. So once again, you pretty much have 90% of your drawing done for you. You just need to copy it exactly the way it looks on the other side. Once again, no funny stuff happens. Yeah. So I'm just going to copy it directly like it is. And really the only thing I'm going to change now is make that now a single bond. Everything else remains exactly the same. Why reinvent the wheel here? Yeah, there you go. So now that I made my double bond into a single bond, I pretty much need to add an H to one and a Cl to the other. In this particular case, does it make a difference? We would want to look at the double bond, and we see the carbon on the right here has 1 hydrogen attached. Carbon on the left has none directly attached to it. That means in this case, the hydrogen should actually end up on the carbon on the right. And then the Cl would end up over there. Any questions on that one? Okay, looking at the second one, once again, I'm going to be concerned with just right there. And I'm just going to make it into a single bond. I'm just going to copy what's in front of me. Exactly the way it looks, single bonding it though, obviously. In this case, we're adding basically 2 hydrogens, which is a symmetrical addition, which basically means it doesn't matter. They're both getting hydrogen in this case, right? So throw a hydrogen over here, throw a hydrogen over there, and you are done. Yeah. Any questions on that one there? All right. Lastly, once again, the only thing I'm interested in is actually the double bond action happening there. So once again, nothing changes. It doesn't open up and wave to you or anything like that. It stays closed. So I'm just going to draw it exactly the way it looks without the double bond in this case. I still need my methyl group that's hanging out there as well. In this case, though, we are adding water, which is unsymmetrical. So that's an H and an OH. In this case, doesn't make a difference where the H ends up. Let us super zoom where the double bond was originally, which is here. So this carbon originally has how many hydrogens? There's how many lines going into it? There are 1, 2, 3, and 4, which means no hydrogens on that guy. Yeah. This guy has only 1, 2, and 3 carbons, or 3 lines coming in, which means it actually does have a hydrogen, which means the one with the most hydrogen is actually the guy up there on top. And that is actually where the hydrogen should go, which is ready there, but I'll draw it. And the OH should go there. Yeah. Question on that one there. So once again, we make cyclohexanol there, which is an alcohol. We make an alkene in the second one, and a hydroalkane there. In the last one, haloalkane. Yeah. Are you? Do you mean like I put it on that side? Is that what you're asking?
No, I mean like you put it on another carbon.
No, it's got to go on that carbon. It's got to go on because that carbon is where the double bond originally was. So remember, just like in the straight one, we're taking away the double bond, and that's going to make the opening for those 2 guys to come in. So it does have to go where the double bond originally was. Yeah. Yeah. So even though it's a ring structure, it works the same way as, any of these guys. The only difference is it's in a ring, but you still have to put those guys where the double bond was. That's the purpose of getting rid of it, is to make room for those guys to come in.